Howdy, everybody. My name is Jeremy Rillera,
Howdy, I'm Evan Schlottmann.
My name is Benton Panozzo.
and this is our boat project. So we want to talk about what is this project about. So this project examines how seawater causes rust, oxidation, and structural deterioration in coastal and marine infrastructure. It connects mechanical engineering concepts to coastal environments where humidity, salt spray, and chloride ions accelerate corrosion. Chemistry is involved through oxidation reactions, chloride-induced corrosion, and material breakdown that weaken metals, concrete, and foundations. Essentially, we are looking at the science behind why marine structures degrade and how engineers can prevent it. So our team originally had 4 members, but 1 left, so we continued with 3, those being Evan Schlottmann, Jeremy Rillera, and Benton Panozzo. Evan consolidated ideas and wrote them down. Jeremy focused on brainstorming solutions and technical reasoning, and Benton organized the workflow to keep everything efficient. At first, it was difficult to combine everyone's ideas into a single project direction. We overcame this by reviewing each idea together and choosing the one with the strongest engineering connection. This agreement kept communication clear and made decision making easier. So our initial individual proposals included corrosion of marine structures caused by saltwater exposure, improving fuel efficiency using tidal pattern studies and fluid mechanics, designing cleaner and more efficient ship exhaust systems, material degradation from seawater through rust and oxidation, and humidity effects on mechanical systems through friction and heat. And we decided to choose corrosion of marine structures because it's a major mechanical engineering challenge and strongly connected to the coastal environment. So our first site we looked at is Gulf Copper. So the explanation behind it is industrial machinery and supporting structures near the shore face constant heat and moisture, which accelerates metal wear and rust. Steel frameworks and mechanical parts degrade faster without any protective coatings. And the way that it links to our thesis is that it shows how environmental conditions near seawater accelerate corrosion in buildings and machinery, requiring careful material selection and maintenance.
I will take you through Royal Caribbean Dock all the way through the Texas City Dike, just explaining what causes this oxidation and rust, as well as how it links to our thesis. So, starting with the Royal Caribbean Dock, its coordinates are up top. The explanation is that this dock right here uses steel and concrete just to protect the ships from any damage that they may incur while stopped at the dock, as well as to keep it afloat and keep it available for these ships to use. A link towards our thesis would be that the pollutants in seawater, those kind of help aid the corrosion on the dock, and it, as said on the slides, illustrating structural vulnerability in marine environments. Up next is Shipwreck Summit. Now this is a ship that did wreck, and as you can see, is very deteriorated up in this top right picture. It used a lot of metals and different reinforced stuff, such as concrete, as stated by the slide. It's located out in the middle of the ocean, kinda, in my perspective. But it really is just an amazing example because of how deteriorated it has become from all of this seawater that's causing this oxidation. For the thesis link, the oxidation it inflicts damage on these metals because of just how much it's in contact with them. I mean, you can see it here. It was strategically sunken, I believe, a while ago, and now it's just become this kind of just big old lunk of metal sitting in the ocean. Next up is the Pelican Island Cut. This cut is it's a navigation channel. Ships come in and out. It allows for the safe passage of vessels. So this kind of helps the ships go towards the Galveston ports, and it uses some metals. It was used to it was expanded so that these different ships could come in and just through this little cut. Also, some great fishing over here. Sorry. Using these certain metals provides a passageway that is safe for these ships to go through. So using these metals, they're going to deteriorate, and these engineers just have to find a way to keep these metals up and running so that this passageway stays available to them. And finally, the Texas City Dike. In the top right picture, you can see a lot of emissions coming out. So these harmful emissions, they're just produced here, and these engineers have to find filtration and exhaust systems that will protect our environment, and it has to help it beat the standards that I'm sure these places have to go through. But these filters are they're forced to be made with metals and other kinds of materials prone to oxidation. So, being this close to the ocean, they're gonna get some salt water on it, some seawater, and it's going to be corrosive enough to have it be a real issue. So these engineers have to figure out a way to prevent the oxidation on these.
Now let's talk about scientific evidence and the engineering solutions related to corrosion, especially what this means for mechanical engineers working near the ocean. One major piece of evidence for marine corrosion comes from real-world structures. A great example is the shipwreck Selma in the Galveston Bay, which we saw. Even though the Selma was built out of reinforced concrete, which usually is considered strong, the seawater penetrated the concrete, reached the internal steel, and caused it to corrode and expand. Over time, this led to cracking and major structural failure. This shows how chlorine add-ons in seawater aggressively attack both concrete and steel. For mechanical engineers, this is a huge challenge because any component near the ocean, bolts, frames, turbines, housings, face the exact same corrosive forces. Another important point is that heat increases the rate of oxidation. Higher temperatures give atoms more energy, which speeds up electron transfer. Since oxidation is essentially the metal losing electrons to oxygen and water, heat makes the process go faster. Coastal environments are usually hot, humid, salty, the perfect combination to accelerate corrosion on mechanical systems. This formula represents the basic rusting reaction. Iron corrodes easily because it readily gives up electrons. Those electrons are taken up by oxygen and water, forming iron hydroxide, which is also known as rust. Materials like aluminum, copper, and zinc also have these similar behaviors, meaning they also oxidize in harsh environments. For mechanical engineers, this makes material selection extremely challenging, since using the wrong alloy or failing to protect it can cause components to fail much earlier than expected. When corrosion weakens structures or machines, it also releases metals into the ocean and increases maintenance costs. Mechanical engineers respond by testing corrosion-resistant alloys, designing structures that can handle seawater exposure, and studying how pollutants react with metals. Engineering solutions include protective coatings, corrosion-resistant alloys, and cathodic protection systems that slow down oxidation. Our proposed solution is a multi-layer protection strategy: corrosion-resistant metals, anti-oxidation coatings, localized cathodic protection, and environmental monitoring to detect early corrosion. Overall, marine environments are some of the hardest places for mechanical engineers to design in. The constant exposure to salt, heat, oxygen, and water means the environment is always trying to break down our materials, and overcoming those challenges is essential for creating a safe, reliable, and long-lasting coastal infrastructure. Thank you for listening, and this concludes our presentation.